Now, in a principal component analysis, we maximize the variance when we select the basis vector that's associated with the largest eigenvalue. Let's explain why. In a principal component analysis, we have this matrix B that's composed of orthonormal vectors, B1, B2, Bm, where Bi transpose dot Bj is 0 when I is different from j, and 1 otherwise. Now we've assumed here that all of our data has mean 0, so the data is centered. And as a result, that means the variance, we'll call it V1, is equal to 1 over n times the sum from 1 to capital N of B1 transpose xn squared. Now this is the variance captured by vector B1. And we're hoping that V1 has the largest variance, or we're going to define V1, or we're going to define vector B1 to be the vector in B associated with the largest variance, which makes V1 the maximum possible variance. Okay, so this, and again, this is what the variance is equal to because the data has mean 0. So this is 1 over n times the sum from 1 to n of B1 transpose xn times B1 transpose xn transpose. And so that's 1 over n, the sum of B1 transpose xn transpose B1. Now, only the x's are dependent on n, which means B1 transpose times 1 over n times the sum of xn transpose B1 is equivalent to the previous line. But we see the square bracketed term is really the data covariance matrix. So this is B1 transpose S B1. Okay, so this is what we want to maximize. We want to maximize the variance. So we want to maximize V1, which is B1 transpose S B1, subject to the constraint norm of B1 squared minus 1 equals 0. Okay, now if we compute our Lagrangian, L of B1 and lambda is going to be B1 transpose S B1 plus lambda 1 minus norm of B1 squared. So that's B1 transpose S B1 plus lambda 1 minus B1 transpose B1. And now we can differentiate. So dl db1 is going to be, derivative here is 2 SB1, and then minus, because their derivative here is 0, 2 lambda B1 transpose. Make both of those the transpose ones. I got to be a little careful here. Let's make this 2 B1 transpose S instead of SB1. We'll make it B1 transpose S minus 2 lambda B1 transpose, just for consistency. So this has to equal 0, which tells us that B1S is equal to lambda B1. That does not tell us that. It tells us that B1 transpose S is equal to lambda B1 transpose. It tells us that S transpose B1, which is equal to S, I can say that, equal to lambda B1. Okay. Notice that this tells us that B1 is an eigenvalue for S. Next, dl d lambda. Well, this tells us that 1 minus B1 transpose B1 is equal to 0, which of course means that B1 transpose B1 is equal to 1. So getting back to our maximum variance. For this to be the maximum variance, we have to satisfy both of these constraints. So this is B1 transpose SB1 from our equation over there. But B1 transpose times S is lambda B1. So we've got lambda B1 transpose B1. And that follows from constraint number 1. This version or that version, if you like. We know something about B1 transpose B1. It's equal to 1. So from constraint 2, this is equal to lambda. So our maximum variance comes from the lambda with the largest variance. So we maximize V1 by taking the largest eigenvalue. Okay. So our largest variance corresponds to the largest eigenvalue. That corresponds to the B1, which is the largest eigenvector, or the eigenvector with the largest eigenvalue, which means that your maximum variance comes in the direction of the largest eigenvector for S.